My work that I'm talking about here is using a vanadium ion, although you can use other things like that, and I'll give you some perspective about this, that can be utilized to store energy, and it would interface quite well with solar or wind, and we'll say something about that. And one of the challenges you have with these materials that you use for a redox flow battery is the materials themselves have some limitations, and that's what my research is about. So the reasons for that, if you ever heard of these top 10 things, I think if you get a Nobel Prize, you get to say whatever you want to say, and this particular person, he created the buckyball with some other colleagues, and because he did that, he was able to say, I have 10 things that I think are most important in the world, and he lists them, right? So we see the top one happens to be energy, and the bottom one, number 10, is population. And I think, if you have a Nobel Prize, you're probably pretty smart, right? Maybe, hopefully. At least I think that's how you get that thing. Right? All those things. So he listed these things, and I think they're actually pretty relevant, all of these areas that he listed. And when we think about population and energy, if you can look at this little picture, it's kind of hard to see that. Does anyone know what this picture is? This is an overview, satellite view of China. Just a little bit of pollution, right? Just a little bit. And that is what it's like all the time. And why is that? Because they have such a huge population, and what do they need? They need energy, they need water. We heard some people talking earlier about just how much it's changed right during lunch about, 20 odd years ago they're more agrarian, and now they're moving into the cities, and the demands are huge for that, for what needs to happen next. I always wonder if we had a satellite picture of, the US during the Industrial Revolution, what it would look like. I have a feeling it looked very similar to this, just coal burning and all these different things going on. So my work is looking at trying to deal with this in some way, and flow batteries happens to be a way to directly deal with this issue. Now, as I said, I'm a material scientist, and I promise you I won't go into large details into that because I don't want to go outside the box here. But I'm very interested in this very basic idea, and this is where it's related to a flow battery, is basically what you want to do is try to move ions and take advantage of these ions to be able to move them across to store energy. And these ideas go from the flow battery to actuators, to fuel cells, to separations, to water desalination. And my interest is in that area. And again, as I told you earlier on, one of the issues with flow batteries is the materials themselves have limitations, and we'll talk about that. So this is my background and where this is coming from and why I'm talking about it. So if we take energy, we have discharge time, we have system power, and we kind of get a range of different energy and where technologies fit. So here's all the way to kilowatts to gigawatts, to the amount of time you need that energy from seconds to hours, where you're going to fit bulk power to responsing, and you can see this is where flow batteries fits in this very interesting area of very long times over a very large energy window. And you can actually see something up here that we're going to talk a little bit about here, but it's pump hydro storage as well. But you can see the spectrum that's here: flywheels, nickel cadmium batteries, lead acid batteries that are in your car, and all these have different limitations as well as maturity levels. So I'm going to tell you that of the storage technologies that are being considered, the one that is the most popular and the most deployed of all is pump storage hydropower. Has anyone ever heard of that before? Yes, everyone has. So what do we need to make this work? We definitely need a hill, right? We need some elevation to be able to do this. And some of this places, like you start going east in Nebraska, and it's kind of flat. Yes. So there's issues where you can be, and the other is if you're living in New Mexico, the idea of having lots of water isn't there. You might have elevation changes, but you don't have the water. So there's areas where this fits. And within this area, you can kind of see the spectrum here, and this dominates. It's 95% of it, so this is kind of giving you an idea of that. And all these other technologies that we're considering, which I think are important to consider, and hopefully I can convince you of that, fit within this little wedge right here that I hope becomes larger over time. These are where this pump storage hydrogen power is located. So you can see lots of water along here, lots of water, Wisconsin, Michigan. And then I'm originally from Montana, so this is actually Helena. Colorado, I'm not sure why Denver has it, but anyhow, they do, and then lots of water. This is hard to see, so we're going to go through this really quick, but this is kind of gives you an idea, again, what we're talking about. What are the advantages of these systems? And here's a sodium-sulfur battery, and what I really want you to focus on is just this redox flow battery, which is really hard text to see, and I apologize about that again. But this gives you the range at which you're talking about. Kilowatts, 120 megawatt hours. So this thing is quite large in the spectrum that you can operate it at. Technologies that people have actually considered, which I'm kind of interested in. I never thought of this one before. I was reading about it last night, is compressed air energy storage. Has anyone ever heard of that one before? Why would anyone want to do that? I still don't know. But that's one idea, right? Pump air into the ground, and then later on, if it doesn't leak, you take it back out at some other time. It just does not seem efficient at all. But anyhow, that's my feeling about this. And of course, we have those all, and of course, we have combustion turbine, all these technologies. But if we take those and look at them overall in terms of dollars per kilowatt hour year normalized, and this is work that was done by Pacific Northwest National Laboratory, they kind of looked at all these technologies together to kind of look at them. And here's your redox flow battery, which is what I'll talk a little bit more technically about a little bit later on. But you can see where these technologies lie relative to each other. And then here's your pump storage hydropower, which is very low. And of course, if we were all talking about using a lead-acid battery, it doesn't work so well. And then you can see with advancement in technology, you can see how these might change over time as well. If we look at some of the other mechanical, non-based systems, your pumped storage hydropower, compressed air, combustion turbine, these are these technologies that come along with that. And then finally, if you kind of summarize all of these relative to each other, you get an idea that redox flow batteries fit quite well within this little spectrum relative to other technologies, which I hope you appreciate. Now, what I want to point out, though, is this. This is a lot of information right here, and all I wanted to really show you is this down below. All of these technologies have a certain lifetime that they will continue to be able to be utilized. So if you're looking at a redox flow battery, we're talking at least 15 years, and of course, if you work with some of the materials that I've created, it's going to be much longer than that, and I'm going to try to hopefully convince you of that. But you can see that there's quite a large spectrum. So the capital cost, the length of time that you'd be operating these, if you're going to use these to store energy, becomes limited with different technologies. The same is with these non-battery storage technologies, and here's your pumped storage hydrogen. Again, you're talking about something that lasts longer than 25 years. And if you use ultracapacitors, there's about 16. So these are lengths of time. And again, if you look at these, length of time between all these technologies, redox flow batteries are pretty high, and then they fall second to using water and storing that. So that, I think, is a promising technology. Now let's go a little bit of science on you. I have to, as I promised, I have to do that because that's my job. Okay, you gave me 5 minutes, so we're almost done too, though. So this is the very basic idea of what a redox flow battery does. You design some type of material that is selective. So I told you I design selective materials. I design polymers, inorganic materials. But what you want to do is you want to separate the electrochemical potential of something. And so in this case, what we have is some ions of some charge, and let's say they're +1. And as they move across, we then do work. We use electrons to do work. That's what a battery does. And we can reverse this back and forth. And what's cool about it is you're talking about them being incredibly scalable in terms of using ions to be able to do this. And here's a nice little picture to show you why this technology has limitations associated with it. So when I said 15 years, it was because the materials, this separator that you have right here, has a limitation in its lifetime. And so we've been working on trying to design new materials, changing their behavior so that they're stronger and last longer. So let me kind of skip these things right here and just kind of get to the last 2 slides of this. So we were funded to look at that. And we looked at 3 different technologies and materials that people have worked with over time. So we're looking at, and I'm just going to have you focus on this one right here. This up here is showing you nitrogen in here. But if we look at these, we're looking at what's known as an SEM. So we're looking very small, we're looking very close at the material that's designed. So what you want is you want this material right here. pristine, nothing's wrong with it, right? But what happens when you create these materials, they have this interesting, what we refer to as a quaternary ammonia group that's able to move charge. When they're dry, they're great. When they get wet, we know what happens when mud gets wet, right? What happens to it when it dries out? Cracks. Because there's so much stress in the material, it cracks. So if you design something that has limited properties, it will crack. And this is actually a state-of-the-art material that people make. We went back and started looking at how you would process these materials and change the processing conditions of this. We were able to change this material that was very brittle when dry to less brittle to now the material is flexible when dry. And the reason we were doing that is because we wanted to be able to create a material that not only had great electrochemical properties and energy storage, but its lifetime would be far greater than the 15 years that we're talking about. So that would change the game, right, in terms of how you would store energy. And so we were able to demonstrate that. So let me finish with these last two slides here. My idea is, or I'm hoping to convince you that these redox flow batteries are really useful. And if we're trying to marry it with wind and solar, and you're trying to store energy when you actually need to use it, redox flow batteries are very, very good. They're much better than, let's say, a lead acid battery, right? And we can then use them later on when we actually need to use them, whether we're talking about building and distribution energy, etc. Okay? So I'll finish here. And as Henry Ford said, before everything else, getting ready is the secret of success. So with that, I'll stop.
Thank you. And I'm Stonie Cooper, and I'm from the School of Natural Resources. My background is meteorology. I'm not an engineer or a physicist, and I do not have a PhD either. I'm from Nebraska. I actually come from cattle country in the western part of the state. And my claim to fame in the energy world is I used to work as a contractor for the New Zealand Weather Service, and they contracted with the Great British folks who are trading carbon points with Germany and other European countries. And I got to be quite an expert at the retail and wholesale side of how you move renewables across the grid in Europe. So Nebraska has a lot of wind potential. Anybody who's lived here very long knows that. So we were given a project. It was a two-part project with NPPD. And what we're to look at is taking Mesonet data. And I'm the Mesonet manager for the Nebraska State Climate Office. And a Mesonet is just a fancy way of saying a weather network, weather station network. We have 68 weather stations throughout the state of Nebraska. They take wind observations, temperature, relative humidity, and a lot of soil parameters. So the first part of the project was to incorporate the Nebraska Mesonet data into numerical models that are used for forecasting weather events and see if they would change the skill of those forecasts for the wind production side of NPPD. And then the second part was developing some specialized wind forecasting tools for NPPD so that they could have a forecast out to 36 hours as to what their generation potential could be for the various wind farms. And so this is the Nebraska Mesonet that I manage. I have 2 technicians that work for me, but all 3 of us are in the field all summer long maintaining the weather stations. It's not a perfect grid, if you will, as far as the distribution of the sites. A lot of these sites are driven by our clients and their interests. So there's a lot in the Platte River Valley, as you notice. And then when you get out further west and north, they tend to be a little bit more sparse. But what works to our advantage is the topography out there also tends to be more uniform. This is a picture of one of the weather stations that we have. We observe the air temperature, humidity, the wind speed, and direction at 9 feet and at 30 feet. We do liquid precipitation, solar radiation, soil temperature, and then we have a whole bevy of soil moisture products that we do, and then barometric pressure. So the first part of the project, we worked in conjunction with arts and sciences, the geosciences they were running a model at the Holland Center at University of Nebraska, Lincoln. And what they would do is they would run the model without our data, just using the data that comes from the National Weather Service, and then they would run that same model again using our data. So I'm going to skip over this because this is really meteorologically deep. But when we get into it, the regional model overestimates wind speed by 3.4 miles per hour. That is without the Mesonet data. You add in the Mesonet data, the bias improves to where it's only oversampled at 1.3 miles per hour. And now you're starting to get into basically the deviation of the instrument itself. So the best improvement with the Mesonet simulation was seen in central and eastern Nebraska. And that's because forecasting models tend to do better where the topography is uniform. And so out in western Nebraska, those models were already performing pretty well. The greatest benefit to locally generated numerical wind speed forecasts with the inclusion of the Nebraska Mesonet data is at lower wind speeds, and unfortunately they were well below the nameplated generation of those wind farms. So we did see an improvement in the forecast, but that improvement in the forecast occurred at the wind speeds that wind generators are not spinning at. So then our focus was on taking and creating a model output statistic from NOAA's generated forecast data and applying it to the near historical generation profiles on a per tower basis to enhance the forecast. So basically, we're going to interpolate the actual point values for each tower that NPPD had, and then we're going to take the actual generation output and apply that to create a bias correction, then to any subsequent forecast going out. So this is an example of Ainsworth Tower 20, and we're just looking at the forecasted wind. We're not applying the power segment to this. And as you can see over time, and this is for an 18-hour forecast, this is what your output would look like. Then when you apply the power segment to this, and this is taking the nameplated aspect of each individual turbine, plus the historical data from NPPD on how that turbine performs, then you can start to do a comparison. And the whole idea of this is the biggest complaint by big utilities on wind power is the relative variability as compared to coal or gas. So if you can kind of tame the shrew, so to speak, if you can kind of put a little bit of a lid and understand what your potential for production is going to be going out a day, 2 days, it does help you manage the transmission of that power. And that was basically our project. I was going to try to keep mine short because Peter has a lot to say, and I'm sure you guys have a lot of questions for Chris and Peter. And I'm done. Oh, I do have one last thing. I like jokes, and I'm a meteorologist. So what did the one raindrop say to the other raindrop? 2 raindrops are company, 3 raindrops are a cloud.
Okay, so I have the advantage of talking about what actually a lot of other people have done, and I'm just warning you now that I'm going to take credit for other people's work. These are the people who are actually in the trenches doing a lot of what I'm talking about, and I'm going to just give you a sense of what's going on in Nebraska in the way of solar cell research. Okay, so this is the standard solar cell. This is what people sell. It's cheap, it's reliable, and it's going to be tough to beat. You almost certainly aren't going to beat it. This is so cheap that the most expensive part of this is the framing of it. Anything you develop in the way of a new solar cell technology, by the time you get it to market, this technology will be 10 years farther down the road. So then you could say, okay, why bother working on solar cells at all if we have a technology that everybody's using? It's cheap, it's reliable, and it works. And the answer is surface area. It's not just a question of a solar cell, it's a question of how much solar cell area collection do you have. And I don't know if there are any university administrators in the audience, but if there are, after this, they won't like me because I'm going to describe this building recently constructed on the UNL campus as extremely ugly. And the point of showing it is not to highlight how ugly it looks, but the fact that it's got a lot of surface area and a lot of windows. Now, the idea is, suppose you took every single one of those windows, and instead of coloring the windows to keep out the UV light and make the rooms habitable, you colored the windows in semi-transparent solar cells. You add a lot of surface area. Maybe not so much in Lincoln, Nebraska, but in big cities, there's a lot of buildings, right? And the other thing is you can do it on every surface, and you can do it conformally. You can now start printing solar cells on the roof of your car or a roof of a truck, just about anything. So, can you do it? Well, the first thing to understand is that when you talk to the community about solar cells, they'll say, okay, we want to cover the solar cell spectrum. This is the spectrum in the back here. And you want to cover as much of this because you want as most efficiency as you want. Actually, this is wrong. You don't actually want the most efficiency possible, right? The people who are going to sell solar cells or generate electricity from solar cells, they have a different agenda in mind, and it's called making money, okay? And to do that, you need the more current, right? You don't actually care about the nuts and bolts of things like efficiency. So, you can start having flexible memory, and you can wear it, and you can put it on clothes, and in fact, you can turn this around and get luminescent displays. And actually, a lot of the technology developed in Nebraska is actually not being used for solar cells, but displays. And of course, that's exciting because now you can get printable displays on paper or screens, and this actually works. Okay, so this is the standard National Renewable Energy Laboratory in Boulder, Colorado. There's the efficiency plot from the beginning of all the solar cell technologies. And the ones that I am first going to begin with are the organic solar cells that aren't terribly efficient. The big problem with implementing them is not the low efficiency, but the fact that they're actually not very stable in sunlight. And not being stable in sunlight is not a big selling point for a solar cell. So you need to improve the organic solar cells to make them stable. They have to work for a long, long time and survive in harsh conditions like professors beating their heads against them. You need more efficiency. 5% would be not so good. 23% would be better. But if you can make them more stable, it'll win, and you need to stabilize them, and you need a way to cover large surface areas, engineer the solar cell so it can be implemented in large areas very cheaply. What does that mean? That means, can you print them? Okay, so these are organic solar cell materials. These are the basic structures. These are some inorganic systems. And what you want to do is add something to these guys. And here's a bunch of chemistry. Basically, these have large electric dipoles in them. When you add them to the organics, they stabilize the organics. What's better is that they add an electric field to the solar cell material, and this sort of pushes the electricity out of the solar cell more efficient. Doesn't make the solar cell more efficient, but it does mean that the current generation is better. In other words, you get better charge generation. And basically the idea is some comes in from a top electrode that's semi-transparent. You combine the additives together. You have a solar cell, and we've done this. Here's one of these standard organic solar cells in the blue line, basically at zero, which is zero bias. You can see that it's dropped below the zero line. What that means is zero bias current has been increased by adding this additive. That's what you want. And how do we test all of these combinations? Well, I have invested in eBay by going on and buying used cheap Canon printers. We use the CD printer tray, and we fill in the ink cartridges with the chemicals we want to make the solar cell out, and just print solar cells. And the advantage is we can prototype a lot of them very cheaply. You can see we just use them. The students have to know what ink, what solar cell chemical they put into the green tray, the red tray, and the blue tray. But if they can remember that, you can now do different combinations and print them out. And here they are. This is one being run in reverse. You can see it's luminescing green, which is a good color. There's the electrodes on top, and this is sort of very simple mass production. And the beauty of this is when one of the undergraduates who's getting a paper out of this actually drops the Canon printer on the floor and smashes it, I just go into my office and find another one. So you can start filling out the solar cell organic and these additives that increase charge generation, and you can see we filled in a few of these boxes, and there's lots more to go, but this is kind of how it's done. There's another way to create a printable solar cell, which is to create quantum dots. That's a technology that's recently emerged since 2010. You could make inks out of these and print them. This is what's in the NREL literature. I've now corrupted the NREL chart. This is the portion of the NREL chart with the quantum dots. This is Nebraska's best effort. You can see it's slightly better than what NREL is reporting. So they should fix their chart and put Nebraska on there. They haven't, but they should. And you can change the color spectrum by changing the quantum dot size. That has to do with quantum mechanics or actually changing the chemistry. Again, we make inks. We put them into the Canon inkjet printer cartridges. We put them in our cheap Canon printer. The students combine the inks in different ways and make different color solar cells and luminescent displays. Okay, and it's all wet synthetic chemistry, which means that we can make the inks pretty reasonably well, put them in the inkjet printer. This is our favorite luminescent or solar cell shape. There's no particular reason. Nobody here would know why we use this shape, but it looks nice. And there it is. You can't see that it's an N sideways, but there it is. If you look at it too closely, it doesn't look quite as nice as you might think, but the point is it does work. The real thing is efficiency isn't everything. We want them to be transparent, so we're not aiming for the highest efficiency. We want to cover more surface area. We want to do this at lower cost, because then you win. And some of these companies, in fact, this company here, Sol, has actually adopted this technique, and you can buy from them a solar cell printed onto a picture window. Usually office buildings, but you can get it from a picture window. So you can say, okay, you know, that's all very nice. You know, what does that mean for Nebraska? So these are a study of the universities that have innovative photovoltaic research in novel materials for photovoltaics for solar cells. You know, this is going from the least cited, that's universities that some of you may have heard of outside of Chicago. That's a dodgy university that I went to. This is another dodgy university also in the same country, and we're basically second from the top. So I'd like to thank the Nebraska Public Power District, the National Science Foundation, the Nebraska MERSEC, and Nebraska EPSCoR for funding this research and funding this research for my colleagues. But there's a lot of new technologies that are emerging. Some of them are actually being adopted. Don't know quite what that means, but somebody's making money off of this. Okay, thank you very much.
We've got time, a lot of time for questions, so have that.
Yes.
I find your solar cells for windows very interesting. Is that something that you are looking at to improve, make more efficient, make more profitable, more transparent? I mean, is there a lot more room in that area to make it more economically feasible for your big city windows and stuff like that?
Okay, so the answer to that question is I'm a physicist, okay, which basically is synonymous with useless. So the biggest window we've done is some undergraduates who are quite brilliant stole my wristwatch and printed a solar cell on the glass cover of my wristwatch just to irritate me, I think. But it did work, and it did light up an LED if it wasn't under my shirt cuff. And that's kind of the biggest area we've ever done. Now, Sowell has taken this technology, and they're printing solar cells on the windows of office buildings. And I don't think they're doing it out of the kindness of their hearts. I actually think they're doing it because they're making money at it. Now, they're not going to give me their financial statement. I don't think they care about me except as a source of useful ideas to put into their manufacturing process. But they're not the only company that's making money at this. So yeah, you can do it on Windows. Now, they're not the most efficient solar cell. Let me say that's kind of important. And there are several reasons for that. One is you have a big window, you want to look out of it. And if you make it completely opaque to make it the most efficient solar cell, then it's kind of useless as a window. And people don't like that for some reason. So you want it to be semi-transparent, and you still want it to generate electricity. You can make them more efficient. People are doing that. They're printing solar cells on strange surfaces where it doesn't have to be semi-transparent. But Sowell is got probably the biggest inkjet printer in the world now to just do what we do in a Canon printer, but way bigger. But you know, most people would say, well, you don't have to print with an inkjet printer. You can cover a large area with screen printing, and that's probably true.
Right, so the question is, so if we're doing mining, do we want to use a lithium-ion battery in the mine? And then what do you deal with when it's exhausted? What do you deal with the material? Is that the question? So if we went back to that Pagani chart and looked at it, that actually doesn't fit quite where you want it to be. Where you would so if you were asking my opinion, are you asking my opinion what technology would work best there? Or are you asking, how does a redox flow battery based on its volume density is not the best technology for that. A better technology is probably to go with, if I were choosing, and it's been reduced in practice, would probably be a hydrogen fuel cell. Yeah.
Correct me if I'm wrong, but you're asking to compare kind of sustainability concerns of cobalt in lithium-ion batteries versus the raw materials of vanadium in a redox.
So, okay, so if we didn't care what happened, how large this thing was? Is that the question then? Right, so, you know, I didn't show all the different types of metals that you can use for this, but there's other metals that you can use easily. So iron is a redox material that you could use, and that's relatively cheap and readily available for you. Each of these systems have their own electrochemical potentials, and I just happen to choose vanadium for this one. So there's not any particular extra special about it, but you could actually use that instead. Well, lithium is limited in how much is available to us. If we use another metal, and again, what I'm saying here is you can use vanadium, but the idea was simply to look at how the cell functions, but you could actually use other metals besides that. And if you did, then it becomes far more environmentally and far more easily incorporated into a system where it's simple, right? So if I'm using an iron oxide one, then that's simple, right? Iron is not an issue in terms of where we're going to find it. Do we have to go to Russia to get the lithium or somewhere in Africa to get it? But it's readily available to everyone. Is that kind of answer your question, right?
Other questions?
Yes.
I'm totally taken with your 3D printing of these solar panels. Is, in your opinion, is it going to become common enough or easy enough to, say, coat the outside exterior of a car where the metal parts are now, 3D print from a car and putting white tinted windshield to be able to recharge an electrical vehicle to increase distance traveled?
Okay, so this is actually more his problem than mine, because the question really here is a little bit complicated because it's a question of power density. All right, and cars are very, very hungry, and they don't have much surface area. But that said, people are already putting solar cells on the roofs of cars, printable solar cells on the roofs of cars. There's a few experimental prototypes. It's a little complicated because actually you don't want to ground out the whole solar cell. So there's a lot of paint that goes on the roof of the car before you put the ground plane electrode, before you put down the solar cell material, before you put the top electrode in. But the roof of the car is a pretty reasonable surface area, and it tends to face towards the sun a lot because it's up. Okay? The problem is it's just not a lot of surface area. You can make it as efficient as you want, it's just not a lot of surface area.
That's what I thought, like with the truck, the hood of the car, the trunk of the car, all that, depending upon the size of the vehicle and all that.
Right, I think the roof of the car, I mean, it's sort of more of an engineering issue. The roof of the car is easier to do the wiring. The problem with the hood of the car is every once in a while you want to lift up the bonnet over the engine, and you got to get the wires not to break when you do that. And people kind of don't like their solar cell getting disconnected. I think that's a problem that could be solved. I would let Professor Cornelius speak to that a little more because he's got an engineering PhD, but I suspect that's a problem that can be solved. But if you have a hybrid vehicle, right, it will contribute to the energy balance somewhat. But let me say this just in terms of an energy balance equation. What Professor Cornelius was saying about hydrogen fuel cells is actually correct in another sense. If you want to make the most efficient car ever, then you're going to convert your whole power system to a fuel cell system, because the efficiency of burning fossil fuels to power your car is terribly low. And if you're going to get it up close to 50%, you're going to go to a fuel cell economy anyway. That's the way to power your car. I mean, if you can contribute to the power by making a hybrid vehicle and putting a solar cell on the roof, that'll help. But you're limited by the current density you need. You're just using too many amps to drive your car.
So in our current project within PPD, with that forecast, we're still in the middle of that project, but we're providing them with basically the forecast. They're not so much interested in the forecasted wind as the forecasted output, power output. And that's why it became important for us to know what the nameplated generation as well as the power curve for every turbine that's going to be in a field. But we start off with that wind forecast. And right now we're going out 36 hours from the time that models ran. In my previous life, when I actually worked with the Europeans, we're going out 15 days. Because within the numerical modeling world, the weather forecasting world, both the Americans and the Europeans run their numerical model out anywhere from 13 and a half to 15 days. And so in those instances, and what they're really were interested about there was twofold. They were interested in demand, which is one half of the part, and the other part is the generation. So they wanted to know if there's going to be cold outbreaks, or if there's going to be heat outbreaks in Europe, because that drives up consumption. Running air conditioners or running heaters. The other part is what's their generation capability going to be. And the bad part about the summertime, and in Nebraska is no different, is in the summertime when we have the highest consumption because of irrigation and air conditioning from electricity. I'm taking natural gas, consumer natural gas off the table here, just talking about electricity. The problem is that's also climatologically when our wind speeds are the lowest. And that's why, and I didn't do this in my presentation, but I was hoping to get a segue that we can do the same kind of forecasting for wind. We can do the same thing for solar output. We have the same numerical model output for cloud cover as well as the shortwave downward coming radiation. We can do the same kind of forecasting for solar farms as we can for wind farms. Because in reality, when you talk about renewables, it's never going to be a one size fits all. My background in energy also includes the initial net metering bill that was passed in Nebraska. I was part of the team that helped get that through the unicameral. And we were looking at all different kinds of things for renewable because you also have microhydro, you also have biologics. We have a fellow up in Cummings County who has a very efficient hog operation where he burns methane off from his farm and actually feeds power back to NPPD. So it's a multiple faceted thing, but getting back to the wind forecast, the main thing is we have the data, but the data doesn't do you any good if you don't know what your performance was on a per turbine anyway. So you need that feedback from the utility or from even a homeowner who has their own wind turbine. You need to know how much you're producing in order to do that bias correction on that forecast. Did that? Yep. As a meteorologist, this is my playground. And a little bit is going to be political in the sense that within the United States, we pour a certain amount of money into NOAA, which is the overall arching organization that has the National Weather Service, the National Center for Environmental Prediction. It has a lot of these agencies underneath of it. The money that goes into the performance of the numerical forecasting within the United States is just under half of what the British put into their model. And it's for that reason that weather forecasters in the United States look to get that model output from Reading, England, and use that for hurricane. One of the most famous utilizations of the forecast from the United States as well as Europe was for Hurricane Sandy. And these are our own National Weather Service forecasters. When it got down to the nuts and bolts of things and they're trying to predict where is this hurricane going to hit on the East Coast, they pretty much relied on what the Europeans were telling us. And that ended up being the right way to go. It is truly how much money you put towards thing is what you're going to get out of it. Now, there is some technological aspects to that. So the biggest difference between any numerical model is how you initialize it. And all that means is how do you basically massage that observed data, not the forecast data, but the observed, what you actually see on the ground and in the air with balloons and from airplanes. How you massage that to start your model, that's really key to the performance of that model. And the way the Europeans do it is different than the way the Americans do it. And until we fully adapt to the way they do it, which there's no trademark, there's no patent, there's nothing like that, but what it is it's more labor intensive. And so what you have to do is have more people, because what they do is they have a lot more eyes looking at that data, doing quality control on the data coming in than what we do. It gets down to you can't automate every aspect of weather forecasting. And the United States is heading that way. They want to automate everything because it's cost efficient. But the Europeans still have a lot of eyes that are on that data when it comes in. Did that answer your...
Talking about fuel cells, could you talk about hydrogen in Nebraska, if that's a viable option, if there's any movement on that?
So I can tell you that I feel sad because when I left Sandia, that was such a big thing, right? The DOE was all into it, and then we had new administration and we wanted to do batteries. It's like we went backwards at least 80 years to go back. Now we're back. I don't know exactly what happens here, but you have more than one source for hydrogen, right? You can do direct electrolysis of water, and there you go, right? Married to PV or wind. Simple, simple. So the idea of having hydrogen wherever you need it, on demand, could be here.
I will say, though, from a safety point of view, you really don't want to go to a pure hydrogen economy. It's very, very difficult to prevent it from embrittling metals. It's extremely difficult because its diffusivity through all sorts of things is so high from preventing it from leaking, and its ignition temperature is so low. So if you store hydrogen, you want actually a safer way to store it, and if it means even synthetic manufacturing, synthetic hydrocarbons or direct electrolysis, that's going to be much safer. I personally don't want to drive on a car that's got a hydrogen tank underneath it, because I'm driving around on a bomb.
So I want to make fun of that because So when I was at San Diego, we used to blow stuff up. I told you that, right? So if we tried to approve gasoline today, there is no way in the world it would ever be approved, ever. But you're right, the hydrogen has issues, and if we had a different philosophy about it, we'd actually design new types of materials that were compatible with it. That's our issue right now. You're right. The absorption or the actually dissolving of hydrogen into metals actually does occur, leading to embrittlement, and other materials have issues with that. We could look at other technology because if we were going towards that, we would start thinking about designing new materials that were compatible with it, right? We would deal with the issue that exists there, but it is a real one.
All right, I think we're out of time, so please join me in thanking our presenters.